It's possible to calculate or estimate the pH of a weak acid if you know the acid or base dissociation constant, Ka or Kb. For example, let's find the pH of 2 molar hydrofluoric acid. And hydrofluoric acid has a Ka that's around 7.1 times 10 to the negative 4. Now remember what Ka stands for. Ka is the acid dissociation constant, which is basically a specific type of equilibrium constant. Ka represents the equilibrium where the acid is reacting with water to give you hydronium, and your conjugate, which in this case is fluoride. So to find the pH, you start with an ice table, which we discussed in an earlier video. The concentration that's given, whether they tell you or not, is in most cases the initial concentration. A lot of times people call it the formal concentration of the acid, and is given as the initial concentration before any dissociation occurs. For example, 2 moles of HF per 1 liter. Now, as far as the initial concentration of water, we don't care because water is a liquid. It's not going to be factored into the expression of Ka. All right, for our 2 products, if we take this to be the formal initial concentration of HF, we're going to assume that if it's before dissociation, we don't have any product, which you may spot as being a little white lie with hydronium, because you've probably been taught about the autoionization of water. So even pure water's got a little bit of hydronium in it. If there's a pH of 7, then the concentration is 10 to the negative 7. However, the concentration for of hydronium in pure water is so small that we can ignore it for the sake of simplicity. So again, we take that as our initial concentration. Water we don't care about because it's a liquid. We have essentially 0 of each product before dissociation. But once it dissociates or reacts with water, you're going to lose X amount of HF, gain X amount of each product. So our equilibrium is going to be our initial minus the amount we lose during the shift. So 2 minus X for HF, X for each product. So remember, pH is equal to the negative log of the hydronium concentration. And hydronium concentration is going to be whatever X ends up being. So if we can find X, we can find the pH. And again, to do that, we can just use the ice method. So again, the expression for Ka is going to be product over reactant. Again, without water because that's a liquid. Remember, liquids and solids don't factor into K. We have a value for K. And using the last row of our ice table, that gives us X times X over 2 minus X, which is X squared over 2 minus X. So initially you may think you're going to have to end up solving for a quadratic equation because you see that X squared there. But remember, a lot of times you can approximate, especially when it looks like the Ka k is significantly smaller than the thing you're subtracting x from. So here you can see they differ by about 10 to the 5. So for cases like that, it's typically safe to assume that 2 minus x is approximately 2. So that gives you 7.1 times 10 to the negative 4 equals x squared over 2. So that gives you x equal to 0.038. And remember, the for a valid approximation, x has to be less than 5% of what you subtracted it from. So 5% of 2, if you work it out, is actually 0.1. So x is less than 5% of 2, so the approximation is valid. So there's our value for x. And again, the pH is going to be equal to the negative log of x. So you take the negative log of 0.038, and that gives you a pH of 1.4.